This video is brought to you by my friends at Patreon, without whom continuing this channel would be impossible. Earth, our cradle in the black. Our cosseting mother whose wispy skirts have, over the course of history, proven an effective refuge from our frigid, empty reality. Even before we knew of what she truly was, we worshipped her as the primal mother and provider of our sustenance. Such veneration crossed culture, space, and time. Even now, our connection to her is universal, personal, and deep. Some of the more avant-garde civilizations, though surprisingly few, directed their veneration toward the sun, though that relationship would always be more distant. Many would assign powers and personalities to specific stars, or, if they managed the difficult task of plotting their courses over the years, decades, and centuries, the planets. But to date, no one has seen fit to direct such reverence toward the Milky Way. This is understandable, as until a century ago last year, we remained incompletely aware of its nature and of our place within it. That said, it's not like we were unaware of it. The Milky Way's diaphanous expanse is one of the key features of our night sky, and is spoken of by every human culture. When sight is clear and the moon is new, it can be seen cutting a 60-degree swathe through the zodiac at Sagittarius and Scorpius, arcing across the vault, and then intersecting again at Gemini. Across tens of thousands of years, and the whole of the Earth, the stories we have told of the ghostly band and its origin have shared some striking commonalities. Several cultures have seen the Milky Way as a celestial river, often a heavenly counterpart to one on Earth. In Hindi, the Milky Way is known as Akasaganga, or the Heavenly Ganges, while Irish mythology considered it the reflection of the River Boyne, site of the sacred hill of Tara. To the Inca, it was the cosmic river Mayu, source of the rivers of the earth, risen to heaven only to fall again to flood the ground. The joint rising of the sun and the Milky Way in December was thought responsible for the heat of summer. Many Australian Aboriginal cultures also saw the Milky Way as a river, with the dark clouds its waters and the surrounding stars, the fires and huts along its banks. Among the Yolngu people of the Northern Territory, a tale is told of two brothers, one of whom sacrificed his life to save the other when a storm capsized their canoe. Eventually they were reunited in death, on the banks of the Milky Way, as the stars Shaula and Lezath in the constellation Scorpius. This story is echoed in the more famous account, told across the Chinese world, of cowherd and weaver girl, otherwise known as Vega and Altair, whose love the Jade Emperor forbade, and let loose the flood of the Silver River to keep them apart, save for one day a year when they can cross on a bridge of magpies. A legend, believed begun in Armenia, but since spread across the Middle East, describes the Milky Way as a path of straw left by a thief. Today, in Arabic, Albanian, Serbian, Sardinian, and many other languages, the Milky Way is called the Way of Straw, or the Thief's Way. Another legend, likely begun among Uralic peoples but now common across northeastern Europe, describes it as the path of birds, as northern peoples noticed that birds followed the path of the Milky Way as they migrated south. And speaking of south, the Milky Way is more prominent in the southern hemisphere because its brightest regions, corresponding to the galactic center, lie in southern constellations. As such, it plays a far more prominent role in the astronomies of Southern Hemisphere cultures, even to the point of independently constructing images, so-called dark constellations, from the dark dust at its core. The most famous of these images is, arguably, the emu of the sky, common to several Australian Aboriginal cultures, which was also seen as Yakana, the mother llama, by the Inca, and, in a striking cultural parallel, as a rhea, or South American equivalent of the emu, to the Mocovi of Argentina. It is, of course, the story known in the West, from which the ancient Greeks derived the name Kuklos Galaxion, the Milky Circle, and the Romans the Via Lactea, the Milky Way, that has spread the farthest in modern times. Like most ancient Greek stories, it involves a heavy sprinkling of lust, chicanery, and blatant misogyny. Zeus, after raping the mortal Alcmene by disguising himself as her husband, steals the resultant child, Hercules, and surreptitiously gives him to his wife Hera to suckle while she sleeps. The details differ with the telling, but regardless, the moment Hera realizes what's happening, she yanks the child from her breast, causing her milk to spray across the sky. It is from the ancient Greeks that our first inkling of the Milky Way's true nature emerged. In the 5th century BC, the natural philosopher Democritus argued that it was a band of closely clustered stars, a vision of the universe concordant with the atomist view of nature he shared with philosophers like Epicurus. This would not be confirmed, however, until 1610, when Galileo Galilei, armed with his newly constructed telescope, revealed the Milky Way to be, quote, nothing else but a mass of innumerable stars planted together in clusters. Upon whatever part of it you direct the telescope straight away, a vast crowd of stars presents itself to view. Many of them are tolerably large and extremely bright, but the number of small ones is quite beyond determination. He concluded that, quote, all the disputes which have tormented philosophers through so many ages are exploded at once by the irrefragable evidence of our eyes, and we are freed from wordy disputes on the subject. It would be over a century before our galactic perceptions shifted again, thanks to arguably the greatest astronomer of the 18th century, William Herschel. Famous today for discovering the planet Uranus, and thus, in one day, doubling the size of our solar system, William Herschel single-handedly expanded the known universe in almost every direction. He was the first astronomer to identify binary stars, and his mapping of their motions provided the first evidence that Newtonian mechanics operated throughout the universe, not merely in our solar system. He identified the polar caps of Mars, and through observing their expanse and retreat, showed that Earth was not the only planet with seasons. But his most epochal discovery, at least in terms of sheer scale, was a brutally simple survey he undertook over the turn of the 18th and 19th centuries. Its methodology was straightforward. Look at the stars and count them. And in the course of over 800 separate observations, that is exactly what Herschel did. Modern minds might find this difficult to believe, but outside the solar system, knowledge of the universe in Herschel's day, a time when, I remind you, the United States of America already existed, had barely progressed beyond the natural philosophy of the ancient Greeks. Astronomers still viewed the cosmos as Aristotle and Ptolemy did, as a sphere studded with stars. Herschel, who by virtue of having built them himself had access to the best optics in the world at the time, determined to change that perception. For Herschel, the sky was not a surface, but the top stratum of a cosmic geology. In the future, he wrote, we shall look upon those regions into which we may now penetrate by means of such large telescopes as a naturalist regards a rich extent of ground, or chain of mountains containing strata variously inclined and directed, as well as consisting of very different material. Herschel was mindful of the limitations of his time. To get anything like a result, he had to assume that all stars were evenly distributed and of equal brightness, assumptions that would in future prove utterly false. Stars, in fact, vary in brightness by as much as 100 million times, and much of the distribution Herschel viewed in the Milky Way was due to obscuration by clouds of dust. These assumptions would lead to the erroneous conclusion that the Sun was near the galactic center. That said, his was the first attempt to map our universe beyond the sphere of the fixed stars, and it led to a mind-bending realization. To quote Herschel again, "It is very probable that the great stratum called the Milky Way is that in which the Sun is placed. For an eye placed somewhere within it will see all the stars in the direction of the Milky Way projected into a great circle, which will appear lucid on account of the accumulation of stars, while the rest of the heavens, at the sides, will only seem to be scattered over the constellations." For a skywatcher of today, this description seems intuitive. In 1785, it was a revelation. The so-called sphere of stars was an illusion. Our galaxy, or universe as it was then thought to be, was a vast slab of 1 billion points of light, all in motion, and we were just one mote within it. Herschel was not the first to come to this conclusion. English astronomer Thomas Wright had advanced it 30 years earlier, but he was the first to show it empirically. That the Sun was a star had not yet been proven, though it was certainly suspected. Its size and those of the planets in relation to it had been determined by the transit of Venus in 1761. But it would still be the better part of a century before parallax measurements fixed the distances to the stars, so Herschel could only estimate the relative distances. But the lid had been blown off. The vision of the universe established in the time of Aristotle had been finally and permanently exploded. In 1757, a young French astronomer named Charles Messier was on the hunt for Halley's Comet. Of course, no one had yet called it by that name, and there was some suspicion that it would not return at all. Edmund Halley, after observing what appeared to be repeated apparitions of the same comet over the course of 300 years, had audaciously predicted its return in 1758, the first ever such prediction for a non-planetary body in the solar system. And so-called computers, human calculators versed in the new, wild physics of Newton, had broken themselves attempting to fix the precise date of its arrival. The world was on tenterhooks. But the universe continually insisted on killing the mood. At the time, the known denizens of the cosmos comprised stars, planets, comets, and nebulae, or clouds. And danged if these clouds didn't do annoyingly good comet impressions. After seeing his hopes dashed once too often, Messier decided he'd had enough. In a fit of pique at the universe itself, Messier began compiling a catalogue of, things that irritated him. A roadmap of warning signs for prospective comet hunters. The false friends, tempting targets, and celestial charlatans that had so flummoxed him. Apparently not of a poetic temperament, Messier christened his discoveries by number. 1, 2, 3, marking them off as he went. Messier did eventually find Halley's Comet, though because he had trusted the erroneous calculations of his friend and patron Joseph Delisle, not until a month after its rediscovery. In time, he would have 13 comets to his name. But perhaps to his surprise, would attain immortality via his catalogue. After its publication, observers began referring to the objects he had identified by number as Messier 1, Messier 2, and so on, and eventually M1 and M2. M1, as it happens, is the Crab Nebula, now known to be the remains of a supernova recorded by the Chinese in 1054. Messier and his colleague, Pierre Méchain, the demon-haunted surveyor who has a starring role in my video on the creation of the metric system, would eventually catalogue 109 of these irksome clouds, and one double star that Messier included mainly to prove that he'd found it, although they would both go to their graves unaware of what they actually were. Today, Messier's catalogue is known to be a kitchen drawer's worth of oddments. 29 are globular clusters, dense concentrations of ancient stars scattered across the Milky Way's outer halo. 27 are open clusters, loose groupings of very young stars slowly being kicked from their birth creches. 5 are the shrouds of gas and dust cast off by dead stars, including the aforementioned Crab Nebula. 7 are true nebulae, the birthplaces of stars. 1, oddly, is a constellation, though it took until the year 2002 to show that the stars comprising it weren't gravitationally bound. But the largest group, comprising 40 objects, were the strange, whirling visions that, once their structure was resolved, would become known as spiral nebulae. The nature of these strange apparitions would perplex the cosmically inclined for hundreds of years. Some wondered if they might have been solar systems in formation, an idea that survived until well into the 20th century. Both Thomas Wright and Immanuel Kant, a contemporary of Messier's who first realized spiral nebulae were in rotation, pondered if, instead, they may be island universes of their own. Messier himself noticed that, of the 110 objects in his catalogue, 13 appeared to be clustered together in the constellation Virgo, making him, all unknowing, the first to identify the Virgo cluster, the gravitational core of the Virgo supercluster, of which our local group is a very small part. William Herschel, as per usual, outclassed everyone else in his day, and by 1786 had, with the eternally diligent assistance of his sister Caroline, catalogued over 2,000 nebulae. He pondered whether M31, what we now call the Andromeda Galaxy, was composed of stars, but later retracted that opinion. Like Messier, he too noted that certain nebulae appeared clustered in various locations, inadvertently becoming the first to identify the Coma cluster. His speculations as to their formation were solidly based on Newtonian mechanics, and, with the added knowledge of galaxies and their nature, still relevant today. He concluded that, as stars are known to be of different sizes, larger stars would likely attract smaller stars, leading to clustering in one region and absence in another. By 1847, Herschel's son John had catalogued 4,000 nebulae, and in 1888, his and his father's observations were incorporated into the New General Catalogue of Nebulae and Clusters of Stars, John Dreyer's compendium of nearly 8,000 and eventually 13,000 objects. This is why today, every galaxy of note not designated M is designated NGC. Although the debate as to their nature would continue for nearly 100 years, that certain of these nebulae may be beyond our Milky Way was already in contention. In 1848, the astronomer and economist John Pringle Nichol wrote of, quote, superb groups of galaxies separated from each other by gulfs so awful that they surpass the distance that divides star from star. Amid this system of clusters floats the galaxy whose glories more nearly surround us. This could very well be the earliest known use of the word galaxies, plural, in writing. By this time, the science of spectroscopy, the determination of the composition of objects by analysis of their emitted light, was just beginning, and the various nebulae were showing marked differences in their spectra. The majority, such as Orion and the Crab, were gaseous, but the spiral nebulae remained elusive. In 1867, Cleveland Abbe, who would go on to deliver the first ever weather report, noted that the gaseous nebulae had the same distribution of the globular and open clusters, and were thus part of the Milky Way, while the spiral nebulae had a completely different distribution, and so were not. 2 years later, British astronomer Richard Proctor, using Abbe's own data, concluded that the spirals were indeed in the Milky Way. The debate would waffle on for 50 years, leading Irish astronomer Agnes Clark to declare in 1890 that, quote, no competent thinker, with the whole of the available evidence before him, can now, it is safe to say, maintain any single nebula to be a star system of coordinate rank with the Milky Way. A practical certainty has been attained that the entire contents, stellar and nebula, of the sphere belong to one mighty aggregation, and stand in ordered mutual relations within the limits of one all-embracing scheme. The next stage in our understanding of matters Lactean was heralded by a personal hero of mine, Edward Emerson Barnard, whose remarkable life I outlined in my video about his eponymous star. In 1905, while at Yerkes Observatory, he began a series of pioneering astrophotographic surveys of the band of the Milky Way, observing the dark nebulae at its core in unprecedented detail and cataloging 370 of them, which, like the objects in Messier's catalogue, now bear his name. Noticing the similarities in the effects of the dark nebulae on stars to earthly clouds, he concluded that they were, quote, more or less opaque masses between us and the Milky Way. The realization that the dark rift within the galactic band was due to obscuration by dust rather than distribution was a revolution in astronomical cartography. Barnard himself would perform a galactic mapping survey, but, in keeping with the pace of discovery at the time, forgot to publish it for 9 years. To finally clinch the debate, it required the location of a standard candle, an object whose brightness could be determined absolutely. If you know an object's intrinsic brightness, you can accurately determine its distance. The miracle arrived at the dawn of the 20th century with the discovery of Cepheid variables. Cepheid variables are gigantic, throbbing, angry stars that, as they age, have swapped fusing hydrogen for helium. Thanks to the work of Henrietta Swan-Leavitt, an astronomer at Harvard, the throbbing pulses of these stars were shown to be tied to their intrinsic brightness. So by timing their pulsations, you can learn exactly how far away they were. In 1923, Edwin Hubble discovered a Cepheid variable in the Andromeda Nebula. And with that, the term galaxy went from a synonym for the Milky Way to the name of the dominant class of object in the universe. But what of our galaxy? Were we doomed to forever stare into a wall of dust, blind to all save our local neighborhood? Well, it turns out there is more to light than what our eyes see, and radio light has a minimum wavelength longer than 1 millimeter, larger than any dust grain. Thanks to quantum, hydrogen, the most abundant substance in the universe, emits a glow at the 21 centimeter radio line, making radio telescopes the best means to map its motion. In 1951, astronomers at Harvard made the first detection of the 21 centimeter glow, and by plotting its redshift, motion away from us, against its blue shift, motion towards us, were able to determine not only that it was in nearly perfect circular motion, but that motion's speed did not decrease with distance. This was the first hint that much of the galaxy's mass was invisible, and would lead eventually to the formulation of dark matter. That same year, radio observations by Jack Piddington and Harry Minnitt at Potts Hill in Australia, following on from initial observations by Karl Jansky 20 years earlier, identified a powerful radio source in the constellation Sagittarius, which would eventually be identified as our galaxy's supermassive black hole. Today, we know that Sagittarius A star, our inelegant name for that black hole, has a diameter almost as wide as the orbit of Mercury, and a mass equivalent to 4 million suns. 2 plumes, 30 light-years tall, extend vertically from the galactic center, possibly the remains of an interaction between Sagittarius A star and a passing star. Another important molecule is carbon monoxide, which, glowing at 113 gigahertz, can be used to map the larger clouds in the Milky Way at frequencies at which hydrogen is invisible, and temperatures of just 5 to 20 degrees above absolute zero. At the infrared, stars become visible behind dust, and the Milky Way's stellar structure can be seen. Unfortunately, as anyone with an understanding of global warming will tell you, our atmosphere blocks most infrared frequencies, and so the best infrared observatories are found in orbit. Infrared can give us images of stars in formation, previously hidden in their birth cocoons of dust, as James Webb has shown. One standard tool for mapping our galaxy are star clusters. Because stars and clusters are all the same distance, their apparent luminosities are proportional to their absolute luminosities. By plotting their apparent luminosities against a diagram showing where they should be in their evolution, it is possible to glean a notion of their distance from Earth. Open clusters have not moved far from their initial positions, and so can be used to trace the Milky Way's structure. Another effective tracer is O and B type stars. Not only are they very bright, but because they have very short lifespans, they also have not traveled far from their birthplaces, and so give a rough idea as to the galaxy's geography. Mapping these stars revealed that they were confined to curved bands, giving us our first hint of our galaxy's spiral structure. So, what have they revealed? That our galaxy, like 60% of known galaxies, is a spiral. Most spiral galaxies, however, have 2 arms, while the Milky Way, at last count, has 4. This places the Milky Way in a rather exclusive club, as only 4% of spiral galaxies have 4 arms. Much like our Sun, our galaxy is large compared to the majority of its fellows, in the 99th percentile, but nowhere near as large as they can be. It isn't even the largest of its local group. Andromeda, the other major component of our local group, is twice as wide and perhaps 5 times as massive. The main component of our galaxy is a disk 100,000 light-years across and 3,000 light-years thick, revolving at an average speed of 180 kilometers per second. The disk is, of course, defined by the famous spiral arms, where the vast majority of star formation takes place. While opinion on this has swung wildly over the decades, for now consensus seems to have settled on our galaxy possessing 4 major spiral arms. From outermost to innermost, the outer arm, the Perseus arm, the Sagittarius arm, and the Norma arm, frayed at the edges into mini arms and spurs. Our local region, the Orion arm, is a spur of the Perseus arm about 10,000 light-years long. Spiral arms are not believed to be fixed structures, but what are known as standing waves, areas of heightened density that, much like traffic jams, persist even as the material comprising them changes. As gas enters this region of higher density, it compresses into new stars. OB-type stars have revealed that starbirth occurs only within a very narrow band of the disk, just 400 light-years tall. Along an axis from Cygnus to Vela, the disk of the Milky Way is apparently warped, like a melted record. No one is entirely sure what is causing this, but one speculation is it is the wake in the galaxy's dark matter halo caused by the rapid motion of its 2 closest satellite galaxies, the large and small Magellanic Clouds. Smaller stars, ones that have been around the galaxy more than once, are up to 25 degrees off the midplane and possess far more elliptical orbits. Beyond the disk, like a fog of steam, is the halo, home to ancient stars up to 12 to 13 billion years old that occasionally pass through the disk at high relative speeds. The halo is home to globular clusters, dense balls of ancient red giant stars, from 10,000 to 1,000,000 strong, scattered from one end of the galaxy to the other, whose relatively uniform distribution made them early signposts in galactic cartography. To date, no one is entirely sure how globular clusters form. Some argue that they are the cores of galaxies that ours has devoured and excreted. The thick disk, a 30 light-year thick mist of stars surrounding the galactic disk, is believed by some to be the remains of a galaxy digested by the Milky Way, whose core is the gigantic globular cluster Omega Centauri. Like many globular clusters, Omega Centauri has a retrograde orbit. It orbits against the Milky Way's rotation, suggesting it was captured. However, other globular clusters may have formed with the galaxy itself. Not only do many have prograde orbits, but their metallicities, the percentage of elements in their atmospheres heavier than hydrogen or helium, show marked differences across the galactic disk. Inner clusters have higher metallicities, indicating they are younger, while outer clusters have lower metallicities, indicating they are older. This is true across the galaxy. Metallicities below the Sun's orbit are higher than those above it. This makes sense. The Sun's orbit is closer to the edge of the galaxy than to the center, which means there are more stars below its orbit than above it. More stars means more star birth and more star death, which means more stars have created heavier elements in their cores through fusion, and then expelled them into the universe. Another possibility is that globular clusters may be the evolved form of the, not confusingly named at all, super star clusters, dense crowds of young stars, between 100 million and a billion years old, cramming more than 100,000 solar masses into 5 parsecs, or about 16 light-years. Because they are relatively young, they are often hidden inside clouds of dust, meaning they were mostly invisible until the rise of infrared astronomy. The 3 kiloparsec arms are located, as their name suggests, about 3 kiloparsecs, or 10,000 light-years, from the galactic center. The nearer of the 2 arms was discovered in the 1950s, the farther in 2008. They are tiny spiral arms containing just 10 million solar masses of material, compared to about 800 million for the Orion arm, which appear to comprise mostly gas, with little star formation reported. At the center of the Milky Way is the bulge, about 10,000 light-years wide and 20,000 light-years thick. The bulge would dominate any image of the Milky Way if we were viewing it side-on. Spherical bulges like the one possessed by the Milky Way, known as classical bulges, have stars in completely random orbits. The stars of the bulge are predominantly old, between 10 and 12 billion years, which explains why bulges are, overall, reddish in color. However, recent studies have shown that as much as 20% of stars in the Milky Way's bulge are younger than 5 billion years, and that these younger stars often orbit more quickly than the older ones. This suggests that the bulge may comprise 2 separate populations, and may thus be the result of a massive galactic collision. Observations by the COBE microwave satellite in the 1990s suggested that, like the majority of spiral galaxies, our galaxy's bulge may be distended into a bar. More recent studies have suggested this central bar is 15,000 light-years long, 5,000 light-years wide, and pointing toward Earth. Bars are believed to form when stellar orbits, over time, become more elongated. This process is likely inevitable, and a sign of a galaxy reaching maturity. Only 20% of the most distant, and thus earliest galaxies, possess bars, whereas 64% do today. This was, I think, a necessary grand overview of the Milky Way for those, likely many, who are unfamiliar with our decidedly unhomey home. My next video will be a collab and will feature a tourist guide of sights to see, as well as an examination of our galaxy's orbiting entourage, the local group. If you managed to get this far, please remember to like, comment, and subscribe. And, as always, stay curious, fellow seekers.